In this next example, we're going to show how you can check continuity using the real and imaginary parts. So as a quick reminder, there's a theorem, and the theorem goes something like this. It's very similar to the theorem on limits. So suppose you were to write your function, let's say f is a function of z, but we were to break down z as x plus iy, and we were to write f as a real part and an imaginary part. The theorem goes if, well, it's an if and only if, so then f is continuous at some point z naught if and only if u and v are continuous at x naught, y naught. So this is an analogous theorem to limits, follows from the theorem from limits. But what this says is that continuity can be checked on each part. You don't have to, you can reduce it to, instead of looking at, you can think about a complex function as a function from two variables to two variables, but you can think about it as two one variable functions, or to a single variable, and you can check it that way. So let's do an example, and the example is the conjugate function. This is a vertical, well, this is a reflection in the real axis. So we're going to show it's continuous everywhere. So we first observe that if we were to write z as x plus iy, then this conjugate function is x minus iy. So in particular, if we set u to be x and v of xy to be negative y, then that's the real and that's the imaginary part. So now let's pick some z naught to check continuity at. Continuity is checked pointwise. And so for that, what we need to have happen is that the limit as xy approaches x naught, y naught of u of xy is what happens when you plug in x naught, y naught. And we need to check that the limit as xy approaches x naught, y naught of v of xy is the value v of x naught, y naught. Now this is just what we're trying to check, and if this is true, then f is continuous at z naught. That's what that theorem says. So to that end, let's check, let's call this one 1, let's call this one 2. So let's check 1. The limit as xy goes to x naught, y naught of u of xy is the limit as xy goes to xy, x naught, y naught, and u of xy is just the function x. Now as x is getting close to x naught, x is getting close to x naught, so that's x naught. And that is actually the value of u when we plug in x naught, y naught to it. Similarly, the limit as xy approaches, oops, my y got messed up, x naught, y naught, v of xy. Well, what is v of xy? V of xy is the function negative y. So as y gets close to y naught, what is negative y getting close to? It's getting close to negative y naught. And that is the value of v when we plug in x naught, y naught. So since the limiting values of the real parts and the imaginary parts were the actual values, we can conclude from this that both the real and imaginary parts are continuous everywhere. Great. So therefore, f is continuous everywhere. on all of C. So that's what everywhere means, on all of C. And that's how you go about using this theorem to check if a function is continuous.